This is the summary of chapter 4 for the main things you have to be looking for. This chapter is about volatility modeling using daily data. Before, what you should have seen is this model to compute volatility. So this is the one to compute returns. And then the one used normally to compute volatility is this one where you have return squared averaged out over a certain period m. So we have m returns, let's say 250, and then you average them out. Remember that here we consider that the mean is 0, so that's why we don't have it here. So this is the simple variance forecasting model. This is the way it would look around the crisis, so you see, well, it goes up. The second model we've seen is the risk matrix one. So here you see that the variance of tomorrow depends on the variance today and the return squared. And what we're going to do is we're going to introduce this model that is called the Garch model. And the Garch variance model has one difference with the risk matrix one, and is we introduce this constant omega. So now on top of r squared and sigma squared, we also have omega. One of the conditions for this model to hold is that alpha plus beta is lower than 1. What this model is going to bring is, take a closer look at this equation, and here what we're getting to is that it is going to have what we call a long run variance. So this long run variance is basically a variance to which forecasting is going to go towards. And that's very important when we do the forecasting of longer day variance. Where are you going to see that? Exactly in here. Basically when you do the expected value of sigma squared at t plus k, where k is like some return horizon, minus that long run variance, you have that it's equal to alpha plus beta to the power of k minus 1, and then the expected value of the variance for tomorrow, which we already know, it's sigma t plus 1 squared. So basically that would be the long-term variance. Under the risk matrix model, the long run variance is basically the variance of tomorrow. So there's no pushing the variance towards any long run mean. Something else I forgot to say is that this alpha plus beta is what we're going to call the persistence of the model. So in here, the persistence is always going to be lower than 1, since alpha plus beta by definition is lower than 1. Whereas in the model for the risk matrix, then alpha plus beta is equal to 1. So then we have that sigma squared is undefined, and the persistence of the model is going to be exactly equal to 1. So then if we compare the two long run variances, so the first line gives us the long run variance for the risk matrix model, so it's basically the variance today multiplied by the k, being k the number of days, and then this one would be the variance under Garch. And you see that the two long run variances are different. So now we have this graph where the long run variance is equal to 0.00014, and then we see that risk matrix, the blue line, stays flat over the forecast horizon in days, so it doesn't change, whereas the Garch is going to go towards that long run variance of 0.0014. Now the next question is, how do we actually estimate these parameters? So this is the Garch model here at the bottom, and it depends on omega, alpha, and beta. The thing is that the sigma of tomorrow at t plus 1 depends on the sigma of today, and then the sigma of today depends on the sigma of yesterday, and so on and so forth. So if we want to estimate these parameters, we cannot do it using linear regressions or OLS, ordinary least squares. That's what OLS stands for. So then we are going to use a technique called maximum likelihood estimate. So we go back to our assumption, the one we've had from the beginning, RT equals sigma tz, and then if we put z equals r over sigma, then that variable should be IID normal. So then we're going to write the likelihood for one return, so it's going to be, this is going to be the likelihood under the normal assumption. So here you're going to have that r changes every day, and sigma is going to be this Garch model that we put here at the bottom. So then if we have a history of many returns with many sigmas depending on the Garch model, then this would be the joint likelihood of the entire sample. So in here what we're doing is basically for each return and each volatility, we're getting probability of falling under the normal distribution. And what we're doing with those probabilities is we're multiplying them. And the whole goal here is to maximize that likelihood. So to maximize this joint likelihood by changing what? Well, R is going to be fixed. Sigma is the only one that is going to be changing. And sigma is going to change as we change omega, alpha, and beta. The whole point is we're going to use solver to change omega, alpha, and beta. And then as we change them, then this likelihood is going to be maximized. One last problem that we have in here is that here we're multiplying really small numbers. So the whole number, the whole likelihood is going to tend to 0. So what we want to do is, well, let's try to change this from a multiplication to a sum. The trick to do that is to take the logarithm of the log likelihood function, where we get that the maximum log likelihood is going to be equal to the sum of the logarithm of that expression we had from before. So this is actually what we have to maximize. We can drop the first term since it's a constant, so it's not going to help to maximize our likelihood. And then we end up with the maximization of this. Remember here, what it's going to change is the sigma t is coming from a Garch model. Well, you could argue that those returns standardized do not follow the normal distribution. However, there's another property of the maximum likelihood is called the quasi-maximum likelihood. And basically what it says is that you can still use it even if returns are not normally distributed. Well, in that case, what happens is the QMLE, the quasi-maximum likelihood estimate, is going to be not as precise as those from MLE, doing a trade-off between efficiency and practicality. One trick to decrease the number of parameters is to use variance targeting. So basically we have the long-run variance sigma squared, and then what we're going to do is we're actually going to get it from the data, and that's the sigma that we're going to assume. If we set sigma, then omega depends on sigma, alpha, and beta. So then we're not going to have to estimate omega, only alpha and beta. So in the next slide we have an example where alpha plus beta is equal to 0.9999. Now from there you can know that the omega is actually pretty small. It's 0.001. In most of the cases it's actually going to be smaller, so that makes the estimation very difficult. But anyways, we're going to get to that in the Excel sheets. And then the graph from that Garch model would look like this. So we have the Garch variance in red and the squared returns in blue. One of the things with Garch is that there are many models. The very first one we're going to introduce is the leverage effect. Remember that the leverage effect refers to the concept that a negative return increases variance but more than a positive return of the same magnitude. Do not forget that. So in here we're going to incorporate this. How we're going to do it? By adding an extra parameter. So here we're adding this theta parameter. So what you have to realize in this model is if you get a negative return, right? Let's first assume that alpha and theta are positive numbers. So if you get a negative return, here we're going to get negative minus a negative. So negative minus negative, it's going to give us, when we square it, a bigger number than if we get a positive return minus negative. So basically the impact of a negative return is going to be bigger on tomorrow's variance than a positive return of the same magnitude. We'll refer to this model as the N-Garch model or the nonlinear Garch. Another very simple way to introduce the leverage effect into the Garch model is to add this extra term here, the alpha theta I RT, where the I is going to be an indicator function. So an indicator function is going to be a function that takes the value of 1 if the return is negative or 0 if the return is positive. So very clearly sigma is going to increase by more when the returns are negative. This model works if theta is greater than 0, and we refer to this model as the GJR Garch model. The GJR is for the authors that created this model. And the third model that captures the Garch effect is the E-Garch. So take some time to actually find out how this model works and why it actually makes variance higher when the return is negative. And pay close attention to the alpha phi being lower than 1. That's a critical key for this E-Garch model to capture leverage. So far what we have seen is a Garch model that is called the Garch 1-1. So basically it relies on one return and one variance, one lagged variance. We could, in general, we can have higher order dynamics where we have a gauge PQ, where P is the number of terms of return square that we get, and Q is the number of sigmas that we have, lagged sigmas that we have. It's more difficult to have an interpretation of the parameters of the alphas in higher order, alphas and betas in the higher order models. So one of the models we're going to work with, it's an extension of the Garch 1.1, is, well, let's first start with the Garch 1.1, and here we're going to have the Lagrange variance, so sigma squared is going to be equal to omega 1 minus alpha minus beta. Actually, we can get that derivation from if we take the expectation, so take a look at that in the book. And in here, you write sigma squared t plus 1 is going to be equal to the Lagrange variance plus, well, the r squared minus the Lagrange variance and the sigma squared minus the Lagrange variance. So now the main question is, what happens if we take this Lagrange variance and we also model it as a Garch? And that's exactly what we're going to do in this component Garch model. So here you see that the sigma is going to be replaced by a Vt plus 1 is the Lagrange variance. That is going to be time dependent. It's going to change over time. And then here Vt and Vt. And then this Vt plus 1, basically the Lagrange variance, is also going to be a Garch process. One of the interesting things is that this component Garch model can be rewritten as a Garch 2.2 model. Now you see that here it's very difficult to get an interpretation of what the alpha 1, alpha 2, beta 1, and beta 2 parameters mean. The other thing we can have is to add basically explanatory variables. So here we add it. It can be anything you can imagine. So one of the variables that we could add is it that takes a value of 1 if it's a Monday, or 0 if it's any other day of the week. The estimation of all these extended models is still going to be done with the maximum likelihood. It's non-trivial, but still same methodology, so it does not change. You see sigma here. What changes is what you have underneath and the parameters that you have in your Garch model, but the estimation does not change. The next thing we're going to see is how do we compare the models. So we start from basic Garch 1.1 model that has, let's say, 3 parameters. Then from there we move to a Garch 2.2 model that has, overall, it's going to have 5 parameters. So then there's this question, okay, from 3 parameters to 5 parameters, are we actually improving? Is it really an improvement? Is it worth using the Garch 2.2 model instead of the Garch 1.1 model? So what we're going to do is we're going to compute the likelihood values that we get under the Garch 2.2 and those that we get under the Garch 1.1. How are we going to do that? We're going to compute something that is called the likelihood ratio test. It's going to be equal to 2, the log likelihood of L1, L1 being the log likelihood of the Garch 2.2 model, minus the log likelihood of the Garch 1.1 model. So what we know of that test is that the LR statistic is chi-square distributed. And then how many degrees of freedom is going to have? The degrees of freedom are going to be equal to the number of parameters added to the basic model. So if the Garch 1.1 model has 3 parameters and then the Garch 2.2 model has 5 parameters, we increased it by 2 parameters. So then we have to look at the chi-square with 2 degrees of freedom. So we come down here, we look at the degrees of freedom, 2, and then we look at the 1% level, so 2 times the difference of the log likelihood functions would have to be bigger to 9.2, so that the second model is an improvement over the first model. The second way we're going to diagnose it comes from the stylized fact that square returns show positive autocorrelation. So then this variance modeling, when we construct our sigma t, if we get to remove the autocorrelation, that means if we get that the r square, which is the return squared over the sigma square, that's the one we are actually estimating, has no autocorrelation pattern, then that means that we actually have done our job. So in figure 5 we're going to have the Garch with leverage effect, and then we see here that the autocorrelation of square returns is actually positive and decreasing, whereas the autocorrelation of the return squared over the variance under the Garch model shows basically no pattern. I mean, we cannot see that it's different from 0. Another way to check if the sigma we're estimating is actually a good forecast, the target variance, is to run this regression. So we're assuming that here the right variances are squared, and we're estimating it with sigma squared. So if sigma is a good estimator of R squared, then B0 should be equal to 0 and B1 should be equal to 1. So that's one regression we can run to actually check if we're properly estimating our variance. Under the ordinary least squares, that regression we just ran, where we assume that B0 equals 0 and B1 equal 1, so that sigma is a good estimator of R squared, is assuming that our loss function, the mean squared error, is equal to the difference in variables squared. So there's actually a different way of judging whether sigma squared is a good estimator of R squared, and that is what we call the Q-like function. So the Q-like function is a function that allows for asymmetric losses. So basically it's going to give more weight to an underestimation of volatility than to an overestimation of volatility. So this is the Q-like function. So if we go to a graph and we print the two of them, what we're going to get is that the mean squared error is going to penalize both sides. It's going to be equally penalized, whereas the Q-like penalizes more the underestimation than the overestimation of volatility. Why? Well, because if you remember from the value at risk, we prefer volatility to be higher than to be lower. Because if it's lower, we might actually get into a breach for not properly estimating our volatility, hence our value at risk. So this comes to an end. Thank you very much for watching.